Alright, hello everyone. This is our final project for our Arduino real-time altimeter. Pictured here is Evan Agarwal and Taylor Brodine outside a Cessna 172 aircraft. The pilot was Matthew Schoenau, and narrating right now is Max McDermott. Alright, introduction. The real-time altimeter is the name of our system, which we abbreviated as RTA. Our major applications include amateur aircraft, as we saw with our Cessna 172, and it can display our temperature and pressure data in addition to altitude on LCD, or store it to an SD card. We could also use it for action sports, such as paragliding and skydiving, to see the altitude throughout the entire action sport trajectory, in addition to alerting mountain climbers when the air pressure gets low enough that they need to use their supplemental oxygen. So the major system requirements that we had was we wanted our BMP sensor to read temperature and pressure at every altitude below Earth's isothermal layer. So we could use that linear relationship between temperature and pressure to calculate the altitude. And then we wanted to display this altitude in real time on an LCD board, or alternatively, we could save the temperature, pressure, and altitude data to an SD card. So our major hardware and software components was the BMP sensor, which was utilized to calculate the temperature and pressure for various altitude. And then we also utilize a simple linear relationship between temperature and pressure to calculate the associated altitude. And so we could either display that on an LCD board, or we could use an SD card to store our data.
The Arduino system consisted of three main components. The first was a BMP pressure and temperature sensor. The second was an SD card module that could read and write to an SD card. And the third was an LCD screen 16 by 2 that could display alphanumeric symbols. The libraries that were included to run these components and modules included a library for the BMP sensor called SFE BMP 180 and wire.h. The LCD used a library called liquidcrystal.h, and the SD card used a library called SPI.h and SD.h. The BMP 180 takes 3.3 volts from the Arduino and communicates via the I2C comms bus through analog pins 4 and 5. The LCD module is powered by both the 5 volts and the 3.3 volt outputs on the Arduino, and it communicates with the Arduino through the SPI bus. The SD card module requires 5 volts of power from the Arduino, and it communicates with the Arduino through the SPI bus.
So as Evan just said, both the LCD and the SD use the SPI bus. So rather than plugging both of these into the Arduino ports, since that's not possible, we actually had to route the SPI bus, clock, MISO, and MOSI to a breadboard. And then from the breadboard, we could plug in the LCD and SD separately, as you can kind of see in this diagram here. And then the chip select pin was used to select which device we're communicating with, whether it's the LCD or the SD. So that's what the CS1 and the CS2 are in this diagram here. Here are some close-up images of the system itself. As you can see, a lot of wires, partly due to us having to route the SPI bus to the breadboard, and then the LCD and the SD from the breadboard to each of those components. So when we actually tested the system, we found it worked really well. The only thing was the Arduino did not have enough memory to support all the libraries from both the SD and the LCD at one time, so we could either use one or the other at one time. So we decided for the ascent we would use the LCD, and then the descent to use the SD card and log the data, which you'll see later. So here's a video of the ascent in the LCD.
As previously mentioned, the Arduino did not have enough memory to run both the SD card sketch and the LCD sketch at the same time. So our team elected to run the sketch that writes data to the SD card during the descent phase of our test flight. As you can see in these plots of both pressure and temperature versus time over the descent, the trend in the direction that we would expect as we decrease in altitude. As we get lower to the ground, we expect that the pressure increases, and as we know, pressure and temperature have an inverse relationship. And so as the pressure increases, we can see that the temperature decreases. So these plots of pressure and temperature are consistent with our expectation of a descent flight phase. Finally, using the temperature and pressure data that was collected and written to the SD card during the descent phase, we were able to run two different calculations to calculate the altitude at the moment at which each of those measurements were taken. In addition to calculating the altitude based on the data recorded by our Arduino altimeter, we also recorded the altitude as reported by an in-flight instrument, so we could compare the Arduino altimeter calculations to the in-flight instrument readings. Unfortunately, we had some technical difficulties, and the Arduino stopped writing data to the SD card about 180 seconds into the measurements of the descent phase. So you can see, as marked by the green circle on the plot, the Arduino shut off about midway through our descent. We believe that the Arduino shut off due to low battery from the 9-volt battery that we were using. Despite this, we were still very pleased with our data and actually very surprised at how well the calculated altitude from the Arduino altimeter matched the altitude as reported by the in-flight instrument. As you can observe on the plot, for the majority of the data that we collected, the Arduino calculated altitude matches almost exactly the altitude as reported by the flight instrument.
The main application of this sensor will be to give real-time pressure, temperature, and altitude readings at a very low-cost method for amateur pilots. We foresee amateur pilots using this to record this data on the SD cards or the liquid crystal display, and then be able to kind of see and track their flight performance throughout the flight. So then, just a quick overlook at our workload. I, being Matthew, did the Arduino code presentation and I flew the airplane. Max did the Arduino wiring and helped us out with the presentation. Taylor also did the Arduino wiring and helped out with the presentation. And Evan did quite the lion's share of the Arduino code and helped us out with the presentation.
Thanks for watching. We hope you enjoyed the project. Here are some of our references.